Hi, here we are to start lecture part one on chapter 19. So, in chapter 5, we talked about what's called the first law of thermodynamics, where we talked all about heat flow and we defined the heat flow in terms of Q. That's with our calorimetry experiments. And then at the end of chapter 5 lecture, I talked about it's really all about the energy, and the energy not only involves Q, but it also involves W, the work of the chemical process that's taking place. But typically, we just worry about measuring the heat transfer or the enthalpy of the reaction. So we talked about Q being equal to delta H. So that's how the chemist usually defines the first law of thermodynamics. So the second law of thermodynamics is related to entropy, and entropy helps explain the spontaneous process or spontaneous reaction. So spontaneous process is one that occurs in one direction. Simple examples: dropping an egg, rusting of iron, tarnishing of silver, melting of ice. So those are all ideas that you can relate to what we mean by as a spontaneous process. So favorable reactions in chemistry are those that occur spontaneously. So we need to talk a bit about entropy. So what is entropy? So entropy is a measure of the tendency for energy to spread or disperse, reducing the ability to do work. So it's the tendency of the energy, and by definition, energy is the ability to do work. And it's a measure of the randomness or disorder of particles that carry energy. So we say that all things in nature tend toward high entropy, high disorder, and that this tendency is spontaneous, and a spontaneous process is considered irreversible. So when we say things in nature tend toward high entropy, if you think about, what happens when you spray a bottle of some aerosol product, what happens? Those particles move from a very ordered state to a disordered state, and that is a tendency towards high entropy. So if we remember the calorimetry example that we did, so we're going to try and look at how entropy is measured in terms of heat flow, because that's really the only measurement that you can reasonably make. So because it's hard to measure how disordered particles are. So we know that from our calorimetry examples in chapter 5 that heat always flows from hot metal to cool to a room temperature water. And we know that it is an irreversible process. So again, that occurs spontaneously. The heat moves from the hot metal to the cooler water, and we would call that spontaneous. It's irreversible. And so when we indicate whether or not a reaction is spontaneous, it's going to be indicated by a positive entropy. And so how we calculate entropy is based on, just like when we calculate delta T's, delta H's, it's always the final condition minus the initial. So what we know in terms of our calorimetry experiment, that heat can flow. It can flow. It's possible. It doesn't tend to do this, but it can flow reversibly between system and surrounding at infinitesimally small temperature differences. So when we talk about delta S, how we define delta S, It's the heat that could be transferred between system and surrounding if the system were reversible. Just like in your calorimetry example, when the metal went into the cooler water, as I said above, it's a spontaneous process. It is not reversible. It's an irreversible process, therefore spontaneous. But if we could keep the temperature difference between the metal and the water very, very small, then the heat that could be transferred between the system and surroundings could potentially be reversible. And so, under those conditions, at that specific temperature, under those conditions, the delta S can be defined as Q divided by that temperature. So up here I give like a graphic illustration of what that might look like. So if this is your system with a temperature that's a little bit higher than the temperature of the surroundings, then it would move from hot to cool. And now if I have a system that's a tiny bit cooler than the surroundings, then the temperature, then the heat, the energy would flow into the system. So it kind of defines the conditions under which you could measure the delta S of the system. And so the first example that we can look at as to how you would apply this in problem solving would be, let's calculate the delta S of fusion. The delta S of fusion is just the entropy for the melting at 0 degrees Celsius of 1 mole of ice. And so what I would need to know here is the delta H of fusion, which we learned about in the last chapter, what the delta H is. It's just the enthalpy for that process, and we went through the different ways that you can calculate delta H. So if that delta H is a given value or calculated value like we did in the last chapter, and so let's say that this is it here, I know that it's 6.01 times 10 to the third joules per mole, and the temperature that I'm dealing with is 0 degrees Celsius, because that's what I have here is 0 degrees Celsius, but I have to put it into Kelvin. You're always going to work in Kelvin when you're talking about delta S. And so when I calculate it, the value is 22 joule per Kelvin. Units for delta S are always joule per Kelvin. Okay, so here's my second example. And what is the delta S if 50 grams of mercury freezes, given mercury's freezing point of negative 38.9 degrees Celsius, and the heat of fusion for mercury, the melting of mercury, is negative 2.29 kilojoule per mole. So the first thing that I do is I have to calculate the Q value. So the Q value, I'm going to start out with the mass. I'm going to convert it over to moles. Then I'm going to use my delta H of fusion here, being careful to make sure I use the sign. And then, since we're ultimately trying to find delta S, I want to convert over to joules here, and I get my value of negative 571 joules. So now I know if I can find my Q value, which I did above, okay, if I divide it by the temperature, which I'm given as negative 38.9 degrees Celsius, I convert that to Kelvin. So now I divide my Q by my Kelvin, and I get negative 2.44 joule per Kelvin. So now I know the delta S, the entropy for the freezing of mercury. And so to continue here, the key idea for the first law of thermodynamics is that energy is conserved when we're considering the system and the surroundings, because we said, how did we say it? We said Q of the system is equal to negative Q of the surroundings. Well, that's not true for delta S. Entropy is not conserved. You have to consider the entropy of the system and the surroundings together. So let's take a look at another example where you have to consider both. Okay, so the above examples, I was only considering a system. So in order to calculate the entropy change for a system and surrounding, you have to do two separate steps. So when 1 mole of ice melts at 0 degrees Celsius in your hand, so we're going to say that the ice is the system. Your hand is the surroundings. So the process is not reversible due to the high temperature difference, right? Remember we said that you can only consider it a reversible process if the temperature difference is very small. But the temperature difference between your surrounding and your system is high. So what we have to do is we have to find the delta S for the system first, and that's Q divided by T. And so I'm going to take 1 mole times the heat of fusion of ice, which we know from my previous example. And so that's just that delta H of fusion here, the heat for melting, 1 mole. And then I'll divide by the temperature, which was at 0 degrees Celsius, 273 Kelvin. Remember, you always want to keep it in Kelvin. And I get 22 joule per Kelvin for the system. Now, for the surroundings, what happens in the surroundings? Well, in the surroundings, it's 1 mole, all right? This time, the heat is lost by the hand. So the amount of heat that's needed to melt the ice, that's positive there, it's going into the ice. But now the amount of heat that the ice has to take in is released from the hand. And so I'm going to use a negative 6.01 times 10 to the third joule per mole. And then I'm going to divide that by the temperature of the hand, which is, I did a conversion here without giving you a temperature in Celsius. This would be a given temperature of 301 Kelvin. Sorry, I should have given that up here. 301 Kelvin would be the temperature of the hand. And so that's equal to negative, so now I have to keep track of my sign, negative 19.4. So now what I have to do, once I have those two values, I have to find the delta S of the universe. And the delta S of the universe is always the delta S of the system plus the delta S of the surroundings. I take those two values, I add them up, I get a positive value here, which is very significant because I know that a positive value for delta S of the universe is going to be a spontaneous, irreversible process. And if that were equal to 0, the delta S of the universe, then it would not be spontaneous or reversible. And so the second law of thermodynamics tells us that the entropy of the universe increases for any spontaneous process. In other words, that it must be a positive value. And so these are examples: tarnishing, rusting, melting, the decomposition of carbonic acid. So those are all of the examples there. And then the last part of the last piece of this first part of the lecture deals with making qualitative predictions about delta S. So what we know is that increasing temperature or volume leads to an increase in entropy, and it leads to an increase in randomness. So in general, we can say that the entropy of a system increases when gases form from solids or liquids, liquids or solutions form from solids, and another one is that the number of gas particles increase during a reaction. So here I give you a few examples of how you can indicate just by looking at the reaction if your delta S of your system would be positive or negative. So as an example, I can see that if I go from a liquid to a gas for water, I know that gas particles are much more disorganized, so my delta S would be positive. If I take two ions and combine them to create a solid precipitate, that's going from less order to more order, the delta S would be negative. And then the same type of example here, if I react iron with oxygen, I'm going to get this, and my delta S is negative. And then here's an example where if these are all gases, right? So I have gas, and I have gas. So this one is tricky because if I have the same number of moles of gases on either side of the equation, so here I have 1 mole and 1 mole, 2 moles on that reactant side, 2 moles on the product side. So what I really can't tell because I've gone from 2 moles of gas to 2 moles of gas. So I cannot make a qualitative prediction based on the equation. I'd have to do a calculation. So if I go back here, I wanted to go back to this example here. This example here, you might say, well, wait a minute, that's the rusting of iron. The rusting of iron should show as a positive value because it is spontaneous. But the problem here is that you can't always make the prediction based on the reaction. Based on the way this reaction is, since I have 2 moles of solid here, 4 moles of solid on the reactant side, and these gases are what make it very disorganized. So according to the qualitative analysis, I would predict that this would be a negative value because more disorganized here to less disorganized, less random here. So I'd make that prediction, but then if I did the calculation, I would find that my prediction is not accurate. So the predictions work most of the time, but not all of the time. I'm going to stop there.